see the first law which says that the refracted ray, the reflected ray and the incident ray which will all lie on the same plane. There it's basically a conceptual law and we don't need to prove that. What we will prove now is the Snell's law that says that this angle sine I by sine r is a constant. So to do that, let's say that this is a surface AC separating two medium with velocity v1 in this medium and velocity v2 in this medium. Let's say that a wavefront is incident on this surface at an angle of incidence I. Okay. Now I need to determine the shape of the wavefront at time, let's say this time is t is equal to 0. So I need to determine the shape of the wavefront at t, let's say time t is equal to tau, and time t is equal to tau is the time at which this point reaches here. Now as I said that all the points on a wavefront is a source of secondary waves. What I can now say is that this point, this point, this point, all are sources of secondary waves. So at time t is equal to tau, if this speed is v1 in this medium, this distance is what? v1 tau. Okay. Now let's see what distance this wave emerging from this point has traveled in that time tau. Speed here is v2, so this distance, let's say, is v2 tau. Okay. Now if I say that this and these are in phase, that means this is my refracted wavefront and this angle is my angle of refraction. Let's say that this is E, this is P dash. Okay, this point is C. So we have angle ABC, we have angle AEC. Okay, so BC is V1 tau and my AE is V2 tau. Okay, now I can write that the sine of angle of incidence is, write sine I as BC by, this is 90 degree, this is also 90 degree, BC as BC by AC, that is equal to V1 tau by AC. Similarly I can write sine of R as AE by AC. This angle is R, this angle is 90 minus R, this angle is R, so AE by AC is sine R is equal to V2 tau by AC. So I can write sine I by sine R as V1 by V2. Now you know that we had discussed in geometric optics that if the refractive index of this medium is n1 and the refractive index of this medium is n2, that means what? This I can write as n2 by n1 because V1 is what? C by V1 is n1, so V1 is C by n1, similarly V2 is C by n2. Put these values here and you'll see that this comes up to be equal to n2 by n1. So you can say that this is a constant because n2 and n1 are defined for a particular medium. So you see that this sine I by sine R is constant for a given pair of refraction and given pair of two mediums. So this proves our Snell's law. You can also see that if angle of refraction R is less than angle of incidence, that means V2 is less than V1. That means if this is the denser medium, that then the angle of refraction is less and the speed in a denser medium is less than the speed in the rarer medium, which is in contradiction with what was proposed in the particle theory of light. Okay. Also, now since these two are in phase, I can write v1 tau is equal to, let's say this distance is equal to lambda. Now since this and these are in phase, that means v2 tau should be equal to lambda 2. This is lambda 1, so I can write this also equal to lambda 1 divided by lambda 2, which means that the frequency remains constant when light undergoes refraction. Okay, fine. So now let's prove the law of reflection in a similar manner. Let's say this is the surface, maybe a mirror, and let's say this is the incident wavefront at an angle I. Okay, and let's assume that the wave front in this medium has a velocity v1. So this distance is what? This distance is v1. Let's say this distance, time taken to cover this distance is tau, v1 tau. Now from here, if I have to get the wave from here, then I'll have to draw an arc of radius v1 tau, and if this point and this are in phase, then this will be my reflected wave front. Okay, so this angle is 90 degree, this angle is 90 degree, this angle is r. Now in this triangle you see that this is equal to v1 tau, this is also equal to v1 tau. This distance is same, this is 90 degree. So these two triangles are congruent. That means what? All the angles are similar, same. So if this angle is I, this angle also has to be I. That means angle I is equal to angle R. Okay, so this proves our law of reflection. Now, using similar approach, I can find how the reflected or refracted wavefront will look when the wavefronts undergo reflection and refraction from different surfaces. For example, let's take the case of a prism. Now, if let's say this is a incident wavefront, so what will be my refracted wavefront? The refracted wavefront will look something like this. Now, this is because you see that this part of the wavefront, let's say this part of the wavefront has to travel a greater distance across the prism. And since this prism is made of a material which has a denser optical density than this medium, the light wave has a very less velocity in this part. So this part of the wavefront gets delayed because of low velocity in this region. This part gets delayed. Similarly, this part you see has to cover a less distance which has a higher optical density. So only small portion of this part it has to cover, so it will cover this whole distance at a greater speed, and so this will lead with respect to this part. So the shape of the reflected wavefront will be something like this. Okay, now let's take the example of a lens. Let's say I have this lens and light wave is coming like this. Here again you see that this part is thicker than this part, so this part of the wave has to travel a larger distance through the lens, which has higher refractive index or less velocity. So that means this portion will get delayed compared to this portion, and the refracted wavefront will look something like this, appearing to, or it will converge at the focus. Okay, so these are some examples where you can find the shape of the refracted wavefront using either Huygens principle or using your common sense. Okay, so now till now we had discussed the generalized phenomena like reflection, refraction, which can be explained using the wave theory of light. Now let's move on to very specialized phenomena like interference. diffraction, polarization, which can only be explained with the wave theory of light. So let's begin with interference. Okay,